Hello everyone. Welcome to this talk on optimal spacecraft reorientation trajectories using internal point masses. My name is Hiran Saravana and I'm a graduate student at the University of Michigan Ann Arbor, and this work was performed in collaboration with Professor Ilya Kolmanovsky at the University of Michigan Ann Arbor. To provide some background on our work, spacecraft generally utilize reaction wheels, control moment gyros, and other momentum exchange devices to perform reorientation maneuvers and attitude control. And we consider the more general problem of reorientation using internal point masses that can move arbitrarily, subject to the spatial constraints of the spacecraft shape and additional control constraints. We began our problem by assuming linear and angular momentum conservation to derive general equations of motion, and we observed minimum energy and minimum time variance of this optimal control problem. We utilized numerical optimization to solve this problem and find solutions for various combinations of spatial constraints and objectives. To formulate our problem, we considered a spacecraft system consisting of the rigid spacecraft bus and n internally moving point masses, assuming zero linear and angular momentum. We used two reference frames to model the system dynamics. One is the inertial reference frame with the origin at the center of the mass of the spacecraft, and the other frame is the spacecraft bus body fixed frame with the origin also at the center of mass of the spacecraft. The orientation of the spacecraft bus was represented using Euler angles, and we used these to derive the angular momentum in the inertial frame, and setting this angular momentum to zero resulted in the following relations. We subsequently used those relations to derive the equations of motion for the spacecraft. We defined a state vector to be the positions of the internal point masses and the Euler angles of the spacecraft, and a control vector as the components of the velocities of each internal point mass. Because our optimal control problem will be treated numerically, we need to transcribe them into a finite dimensional optimization problem. So for this, we use the trapezoidal method to convert our continuous time equations of motion into a discrete time form. And the use of the trapezoidal method was a compromise between complexity and stability. Euler and RK2 integrators can become unstable for larger time steps and highly nonlinear equations of motion, while RK4, on the other hand, is much more computationally expensive and slows down the optimization process. We considered two different objectives: the minimum energy or energy loss objective and the minimum time objective. The energy loss objective is meant to be a sort of normalized friction energy loss objective. The instantaneous energy loss at each time step j is assumed to be dependent on each mass's velocity, and we neglect the differences between absolute and relative velocities, and we essentially sum over this square norm of the velocities at each time step and at each mass, and then normalized by the number of masses. The minimum time objective is merely minimizing the terminal time at which the reorientation is complete. For the minimum time objective, we impose additional control constraints to ensure that the optimizer doesn't keep arbitrarily increasing the magnitude of the velocities to get smaller and smaller times, because this will essentially mean that the smallest possible time would be zero as the velocities become infinity. Our spacecraft's spatial constraints were merely the spacecraft shape, and these have the form of an inequality. The total mass of all of the internal masses was constrained to be 1 kilogram, so as the number of masses was increased, the mass of each internal mass would decrease. And and all spacecraft shapes that we considered had the same internal volume. For the minimum energy objective, we generally considered two different types of trajectories. One was a trajectory where the initial and final positions of the masses were not constrained, and the other was the constraint that the masses begin at the origin and return to the origin. The trajectories for this minimum energy loss objective were generally non-unique. We found that changing the time step resulted in different trajectories with the same energy objective, and that masses generally moved in the plane perpendicular to the axis rotation from Euler's rotation theorem, which is also called the principal axis, and this is the axis of the single rotation that's equivalent to the full rotation represented by the transformation matrix between the body fixed frame and the inertial frame, evaluated at the terminal angles. For this spherical spacecraft shown here, the masses move together. On the other hand, if we constrain the initial position of the masses such that they begin from different locations, they attempt to move along the plane perpendicular to this principal axis, and they also try to move together. In the cubical spacecraft, the internal masses also attempt to move along this plane perpendicular to the principal axis, but they aren't able to quite do so due to the constraints of the shape of the spacecraft. We found that for non-convex spacecraft shapes, such as a bow tie shape, we required additional constraints. This is mainly because we observed switching behavior where the masses instantaneously move from one side of the spacecraft to the opposite side from one time step to the next. Due to the discrete nature of the problem, none of the previously existing constraints are technically violated, but the path joining the positions of the masses lies outside of the spacecraft. So to deal with this issue, a set of points along a line between positions at any two consecutive times were constrained to lie inside the spacecraft. And such constraints are required to ensure that the masses do not move outside the spacecraft between two consecutive times. Here we have an example of a minimum energy trajectory for the bow tie spacecraft, and we see here that the masses no longer attempt to move along the plane perpendicular to the principal axis. Minimum time trajectories are much less regular. We observe here that the control exhibits a switching behavior between the maximum and minimum values allowed by the constraints, which results in the masses no longer moving along the same plane. We also studied the effects of an unequal distribution of mass between the various masses for a three-mass system. A single mass was increased while the other two masses were decreased to still maintain the total internal mass at the same value. We observed that the minimum time remained unaffected, but the minimum energy decreased as the mass became more concentrated. This is because the energy loss in our model is not proportional to the mass, which means that the optimizer will naturally move the largest mass more because it allows for the greatest effectiveness in reorienting the spacecraft. The largest mass naturally has more momentum, so concentrating the mass results in less energy loss. The other masses, as a result, are moved less while the heaviest mass is moved more. For the minimum energy case, we observe that masses generally tend to move together in convex-shaped domains, and they tend to move at the largest radius permitted by the spatial constraints near the plane orthogonal to Euler's axis of rotation for any given maneuver. For example, we observe that for the cube region, the internal masses were able to achieve smaller minimum energy objectives than the spherical region, even though their volume is the same. This is due partly to the geometry, because the side length of the cube would be smaller than the diameter of the sphere. So the principal axis for the specific terminal angles would allow the masses to move a larger distance from the origin for the cube than for the sphere by forcing the masses to rotate at an angle. Additionally, we studied the minimum time trajectories, which were much less regular, and we observed that a type of switching behavior occurred where the control would switch between the maximum and minimum permitted values by the constraints. We also observed additionally that the energy for the minimum time is significantly higher than that for the minimum energy case, almost 2 orders of magnitude. The results motivate research into the design of novel attitude control actuation that could rely on internal masses that could be electrically actuated, possibly, and move in a volume within the spacecraft as shaped by these minimum energy or minimum time trajectories. That concludes this presentation. Thank you for listening.